There we go. So let me start off with maybe some surprising things. And I know that, that maybe Matt and Neil won't be as surprised by this as some of you all, but maybe a little bit. I'm going to start off with this following game. And so let me see how good my artistry is. What am I drawing?
I assume it's a chessboard.
Well, see, that would be correct, except I'm a Tennessean, so it's a checkerboard. We're not like Balkans or anything there. So I'm going to play this game, and in fact, I am going to use checkers, and I'm going to take checkers, not to scale. My brother and I used to play with these things, and we never used them for playing checkers, but we'd mess around with them. And I'm going to make successively larger towers of checkers on this checkerboard. Each of my checkers are 1/4 of an inch tall, so they're very small. It takes 4 of them to make an inch, 48 of them to make a foot. And I'm going to do this. I am going to put 2 checkers in the upper left-hand corner, and I'm going to double it every time. 4, 8 checkers, stack of 16 checkers. And of course, at this point, the 16 checkers is only 4 inch high. And I keep going like this, filling it up higher and higher until I put down there in the lower right hand a stack of checkers that is 2 to the 64th checkers high. So here's a question. I think we can all agree that that's a big stack of checkers, right? But how big? Round figures. How tall is that stack of checkers? Anybody want to ballpark it for me?
I'm going to make a guess, unless anybody else wants to jump ahead of me.
Guess away.
Yeah, bigger than the universe. That's what I was going to say.
What's that now?
I was going to say bigger than the universe, but someone got to it before me.
Well, see, you ruined my surprise because it's not quite that.
Right?
But I mean, see, I'm dealing with a more sophisticated audience now. This is actually a very good sort of general interest talk, because most people you can surprise them by saying, is it taller than the Empire State Building, right? Which most people would find rather surprising, right?
7 trillion.
Actually, this stack of checkers, which, by the way, 2 to the 64th is a fairly tame number, right? This stack of checkers actually is 12.4 light years long, as a matter of fact. So this 2 to the 64th checkers will reach to the nearest star that's not the sun, which is about 4.3. It'll there and back and then back again. So in other words, if I stood this from the ground and stood at the top of it, and I shone a flashlight back down to the bottom of the stack, it would take about 12.4 years for the photons of light from my flashlight to reach the surface of the Earth, right? Which really kind of boggles my mind, because this number is represented pretty simply. And in fact, it is the y coordinate of the function y equals 2 to the x only when you go 64 units over. But this number is very big. And
but Jim, it's surprisingly small to a mathematician, right? We
well,
get it in the universe or something, so it's surprisingly small.
Well, right. Well, from that argument, all numbers are surprisingly small, right? The order of the monster is surprisingly small, right? But so here's another let me change this exercise a little bit and try to keep things into perspective. So by the way, does anybody own a calculator these days? I don't know if anybody does that anymore or not, right? But my dad, oh, Matt's got one. My dad was an architect, and I used to go over to his office when I was a kid because they had like these really what I thought were just nifty calculators, and I'd play around with them and this and that. And I became sort of fascinated by the factorial button, little exclamation point, so I could enter an integer and press it, and all of a sudden it would get very big. And so this was back in the 80s, I guess, or maybe 70s, when I first started doing this, playing around with my dad's calculator. So these are sort of primitive calculators by modern standards. And so, so here's something for, I don't know if anybody's ever observed this, but there was something special about 69 when I'd play with the factorial button on my dad's calculator. Anybody know what it is?
It would be the last number before once you go to 70 factorial is an error because it's over 100 digits.
That is correct. 69 factorial, I found by trial and error, was the smallest number that I could put in my dad's calculator and press the exclamation point, and it would actually give me a legit number, or at least something I thought was a legit number. It would give me something times 10 to the 98th, and then 70 factorial, it would exceed 10 to the 100th power and be gone. 10 to the 100th power is kind of, well, that's something we'll come to in a moment, but that for some reason, the calculators, they just couldn't handle it. So let me recouch my original problem here, and let me play the same game with checkers, only this time I'm going to do it instead of doubling every time, instead of using an exponential, I'm going to use factorial to stack these up. And let me point out that the first stack of checkers is smaller than the original, because what I'm going to do is I'm going to start off here with 1 factorial checker, so there's only 1, 2 factorial checkers, so there's only 2, and 3 factorial, so there's only 6, and I end up here with 64 factorial checkers. Now, again, the checkers are a 1/4 inch tall, and I want to know roughly how high that is. Now, let me point out that 64 factorial is nice because 64 is smaller than 69. So this is a modest number that even my dad's old-fashioned calculator from the 70s could handle as far as giving me a number. Now, how big's this stack? This one
Those two are bigger
is
than the universe.
this one is much, actually, I think that is probably correct. So let me put this in another term. That stack of checkers, 64 factorial at a 1/4 inch thick, is very big. And so let me put it in, let me kind of put this in a different perspective. How many of you are familiar with the Andromeda Galaxy? Right, you know, it's this fried egg looking thing. It's a companion galaxy to the Milky Way. You know, you've seen pictures. It's like Utah. You've seen pictures, right? And so it's a galaxy. It's very far away from us. It is roughly 2.5 million light years away. And so that's a long way, right? Because light travels 186,000 miles per second. So that's basically 7.5 times around the Earth at the equator every second. And so the amount, a light year, very long. In fact, to give you perspective, the sun is 93 million miles away. It's about 8 light minutes away. The Andromeda Galaxy is about 2.5 million light years away. And actually, it's about half the size of the full moon in the sky, which is amazing how big it is. But anyway, our stack of checkers will reach to the Andromeda Galaxy and back 17 billion times. That is a lot of checkers. And we'll never be able to verify that this works because the amount of subatomic particles it would take to make that stack of checkers is more than the amount of stuff we have in the universe. So, but this is an old-fashioned number that fits on my dad's old-fashioned calculator, and it's really sort of, it kind of boggles the mind how big it is. Let me give you something that's a little bit closer to home, perhaps. Starting with these, I've got two more of these kind of large numbers before I'm going to do a little probability. So y'all have all seen this, correct? Rubik's Cube before. I used to do the North Dakota State Governor's School for many years up there. And one year I bought a bunch of Rubik's Cubes because I taught these high school kids group theory using Rubik's Cube as a teaching tool. And kind of a funny thing that made me realize the way the world works is in Fargo, North Dakota, before I ever did this little project, you could not find a Rubik's Cube in Fargo. And so I went to a toy store in Fargo and I ordered 25 Rubik's Cubes. You should have seen the clerks. They said, 25? Really? Yeah. So I got 25 Rubik's Cubes and I got my order in and, gave them to the kids for governor's school to, teach them a little group theory. And not a month after that order came in, you could find Rubik's Cubes at every small store in Fargo. So they all must be spying on each other or something, because you could find Rubik's Cubes in the gas stations after that. But anyway, the packaging that the Rubik's Cube came in, when I first did this governor's school thing and got that big order, is they all came in a little plastic box that said billions of combinations, only one solution. You will never in your life see such an overly exaggerated, undersold advertisement, right? I mean, what do advertisements do? They're supposed to tell you, I mean, my God, the guy that sold me my car told me how great it is, and now it's like, basically a McDonald's dumpster with an engine in it, right? I mean, everybody oversells and advertises, and they totally blew it on the Rubik's Cube. Billions, well, that is true, but it is the great missed opportunity. The number of combinations on this Rubik's Cube, and actually, I will, let's see here, right. The number of combinations on a Rubik's Cube is actually very large. And let me say something really quick about that. A Rubik's Cube looks something like this. And it's, whoops. Let's see here. It's divided up. I didn't even change colors for me. So again, you all go away. There we go. So there are 8 corner pieces like this, and there are 12 side pieces that look like this that only have 2 colors on them. Now, if you took that cube apart, and so you take a screwdriver and you take the cube apart, which, by the way, if you ever want to cheat on the Rubik's Cube, that's the way to go. Don't ever take the stickers off. It doesn't work well for you. And in fact, taking it apart with a screwdriver, you see how it works, and it's kind of an interesting little piece of engineering. Anyway, so what you have is you have 8 corner pieces. So you take the cube apart, you let the little pieces fall, the ones with 3 colors and the 2 colors all over your table. And you go to put it back together, but then because of your sinful ways, because you cheated on the Rubik's Cube, you go blind. And so now you're putting it back together blind. Well, you feel your way putting it back together. And if you pick up a corner piece, it's got 3 colors on it, you're not going to be able to put it where a side piece goes, right? And so there's actually 8 factorial ways, geographic places, I should say, where you can put a corner piece. And there's 12 factorial ways that you can put in the side piece. But every corner piece, there's 3 ways you can put it up in there, because there's 3 colors that could be facing up, say. So that gives you like 3 to the 8th ways to arrange the way to put the corner pieces in. And each side piece has 2 ways you can put it in. This is the number of arrangements of a Rubik's Cube if you take it apart and assemble it when you're blind. Actually, the number of combinations on this really is 11 factorial, 8 factorial. This is the number of combinations that you can get if you don't take it apart. So if you start with a solved cube and you just muck around with it and never take it apart. So notice that basically it's the previous figure divided by 12. That means if you put a Rubik's Cube together blind, there's only a 1 in 12 chance that you're going to be able to solve it without taking it apart again. So always put it back together solved, because there's not a very good chance you're going to get lucky. But anyway, so here it is. Rubik's Cube, that's the number of combinations. And this comes to about 43, well, it's 4.3 times 10 to the 19th, right? Round figures, right? Now, how many is this? Well, 4.3 times 10 to the 19th is less than Avogadro's number. And any of you that have had a chemistry class, either in college or in high school, you see Avogadro's number and computing the number of moles or the number of atoms in a mole. That number is bigger than this. 4.3 times 10 to the 19th seems pretty humble compared to the other numbers we talked about, but how big is this really? Well, let's suppose, now the Rubik's Cube is supposed to be the best-selling toy of all time. So let's suppose, just for giggles, that we take every, well, the population of the country's probably changed a bit, but I just did this computation with 300 million. Let's say we take 300 million people, the number of people in the United States roughly, and we put them all in a line, and we all give them a Rubik's Cube that is solved. And we say go. And every second, all 300 million people turn the cube. Every second, all 300 million people get a new combination on the cube. All 300 million get something different. And nobody is repeating anything anybody else is doing in line ever. So every one of those 300 million people, every second is generating a different new combination on the cube. And suppose we have a large computer that is somehow recording all these different combinations and cataloging them somehow in its data banks. If you let this continue, where all the people are sitting there scrambling the cubes, every second, 24 hours a day, for 40 years, and then you stop it, and you look on the computer, you will find that you have cataloged less than 0.9% of the number of combinations on the cube, right? So like 0.87%. So not even a percent after all that time. So even this humble number is quite large. And I guess I think that probably this is this next one is probably one of my favorite examples. When I was up in Fargo, I had a very good friend, and she was like, she had a couple of kids, and she was like best mom ever kind of person. And you know, she was always kind of educating her kids and getting them like these kind of really progressive books about science and learning and dinosaurs and everything under the sun. And she got them kind of a book for like, you know, maybe age group 8 to 11 kind of on math. You know, and of course I dug that because, you know, it's always nice to see people getting their kids to have a positive spin on math and showing them all that sort of thing. And I read through it because it was kind of fun. And there was a place in the book where it was talking about large numbers. It wasn't that extensive, but it talked about a Google. Anybody know what a Google is?
10 to the 100.
That is correct. This is a Google. It's 10 to the 100th power. big number,
Of
right?
course, the
And if,
interesting question here is why is it spelt differently?
this one actually, the first place I ever heard about this is when I was a kid on Cosmos. Remember that Carl Sagan's Cosmos thing, and he attributed to I think it was a computer science. It was the nephew or son of somebody, I think, in computer science that coined the term, and it just kind of stuck. Called it a Google. I'm not sure how the spelling is, because when the website Google first came out, I can remember when that, and I thought it was a takeoff on this.
I think there's an interesting backstory on why, yes, it is a takeoff, and no, it's not spelled the same.
Right. And so I don't know how. I don't know how common this one is. Again, I heard this one on Cosmos as well. Anybody know what a Googleplex is?
10 to the Google.
That is correct.
I think it was the company was a misspelling of the original Google.
Oh, no kidding. They got it wrong, huh?
Mhm.
That's funny. So, a Google is, well, I mean, if you're patient enough, well, you can write that down, right? I mean, it's 1, and then you got to write 100 zeros, right? And we can all be patient enough to do that if we want to, I don't know, impress somebody. A Googleplex, good luck, right? Because that is 1 followed by a Google's worth of zeros. And let me point out that if you talk to most modern physicists, most of them say that there's in the neighborhood of about 10 to the 80th subatomic particles in the universe. And I've never seen an estimate that goes over 10 to the 87th power. And what that means is, even if you could turn every subatomic particle in the universe into a digit, you don't have enough stuff to write a Googleplex down, right? So there it is, a nice symbolic form, but this is a number that is sort of beyond comprehension. So anyway, in my friend's book for the children, the author talked about giving a talk about numbers, and it wasn't like a talk to y'all. It was more of a general audience sort of thing. And one of the persons who was listening to the talk raised their hand and said, "Well, just how big is a Google?" And the author wowed his audience, and he said this in his book. He wowed the audience by saying, "A Google is greater than the number of raindrops that have fallen in all of Scotland in the past century." And when I read that, I just started laughing, and my friend said, "Why are you laughing?" I said, "Well, of course, the author is correct, but it is another great opportunity, another great missed opportunity." And she said, "What do you mean?" And of course, the gauntlet was thrown. And so I did some computations. And so I had to do a couple of things first. So let me give you some facts about Scotland. We're going to suppose Scotland is 32,400 square miles. Actually, that's bigger than Scotland. Scotland is a little less than 31,000 square miles. Anybody want to take a wild guess why I didn't say 31,000 instead of 32,400? Why did I round to that?
Divisibility properties, perhaps?
That's right. It's a square, right? So I sort of rounded up to the nearest square. So this is 180 miles quantity squared, right? Now, then I had to guess on the fly. And, I don't know how much rain, I don't know what rain density is. So I made something up. Turns out I kind of messed this one up. I assume rain falls. And I don't want to make a liar out of myself, and so I don't want to over exaggerate things. So I'll assume that it's a strong rain, so it doesn't. I'm going to assume it rains pretty strong, so it doesn't take a long time to get a Google, right? At 200 drops per square inch per second. This is where I messed up a little bit because I looked it up later. Apparently, some estimates classify a torrential rainfall as 113 drops per square foot per second. And so basically what I have done is I have created a scenario where God has a Scotland-shaped fire hose and is blasting the country with water. That's essentially what's going on here, because you got 200 raindrops per square inch per second. All right. But nonetheless, we'll go with this. Now, what I did then is let's just compute. I computed the number of raindrops at this rate, how many raindrops fall in Scotland per year, and I computed this, and it was something along the lines of about 8.2 times 10 to the 23 drops of rain, even at this fire hose rate. And so now all you got to do is divide to see how long it will take at this constant rate of rain that never stops, how long it takes to get a Google of drops. And this is about 1.2 times 10 to the 76 years, as a matter of fact. And so for some perspective, that is 870 billion times the age of the universe. And I mean the age of the universe like on the Big Bang Theory and not like school in Kansas. So that is a long time to get a Google of raindrops. Okay, any questions so far? And let me see, how many people do I have in here? Because this will, this next little bit here.
Is right at 23 participants.
Right, and that's kind of, and actually, I think Neil knows where I'm going with this, and so this is like the Hunger Games. Maybe the odds be in my favor. How many of you have heard of the birthday problem? Maybe a number of you have. Let's see if I fail at this one. This is the old, if you tell somebody, all right, I've got a room with, say, 30 people in it. What are the chances that at least 2 of them have the same birthday? And for the purposes of this, talk, I'm going to forget about February the 29th, and I'm going to forget about birth years, right? It's just the day, not counting February 29th. What are the chances that at least 2 of them have the same birthday? Now, most naive people will do something like take the 30 people in the room and divide by 365 and say, oh, it's pretty small, right? But we all here probably know that it is larger than that, right? And so actually, let me go through here a little bit. I am kind of curious. I am going to, I'll go down my list here, or at least as you appear on screen, and I'm going to ask you for your birthday and shout out your birthday when I call on you. And if anybody else has the same birthday, then say, okay, just pipe in and tell me that you've got the same birthday. Okay, I see Adam first.
May 3rd.
May 3rd. Okay, Dakota.
7/11.
7/11. Neil.
March 29th.
March 29th. Matt. Oh,
Sorry. What am I doing?
your birthday,
August 17.
August 17th. And Aditha,
Yeah, July 14th.
July
Sorry,
14th.
my video for some reason. Yeah, July
You
14th.
Chung.
Yes.
May 7th.
The 7th. Kuzman. Maybe not with us. David,
October 20th.
October 20th. Tori,
April 18th.
April 18th. Ania,
December 25th.
Ma.
Oh, me?
Yes, Aman.
Okay. Yeah, April 5th.
Leo,
April 26th.
Lucille,
July 27th.
27. Stephen,
February 21st.
I've already got a month. Yeah, these things moving around on me. Cynthia,
April 7th.
what 7th?
April.
April 7th. Okay, Jay,
December 21st.
Killian,
March 31st, and then
I'm Ryan. I'm here, and mine is June 25th.
oh, okay, all right. And let's see, did we get Killian?
yeah, mine was March 31st.
Okay, Dan,
Can you hear me?
September 1st.
September 1. Timothy,
September 4.
and David.
September 23rd.
Huh, well, that's mine. No, I'm kidding. It's not. This is actually the first time I've ever given this talk, and I didn't pair up on anybody.
But
How
I think
many
somebody
people-
matched. I think somebody matched Amin's birthday.
Oh, did somebody match it? Oh, okay. Well, then I guess I'm undefeated. How about that? I didn't realize that. Okay, so we have right now 23 people in the room, and Neil knew the magic number because that's actually the point where we just go over 50%, right? So I was 50-50 on that. But the fact of the matter is that, well, so how do we do this? How does this birthday problem work? Well, and this is going to come up in just a moment. Let me move on here. So here's my beautiful rendition of the birthday problem. Okay, when you've got a whole bunch of people and they all look extremely hungry. When you put the first one in the birthday room, the chances that he has the same birthday as somebody else in the room is 0 because person's the only one in the room. Then when you put the second birthday in, what is the chance that they don't have a birthday same in common? Well, the new person in the room has to hit any of the 364 days that the first person doesn't have. Now, when we move the next person into the room, what are the chances that nobody has a birthday in common? Well, this person just has to hit the other days that the other two doesn't have. And then the next person and so forth. Now, these numbers that I'm multiplying are very close to 1, but they're not 1, right? And anybody that's ever played around with a calculator, is anybody ever, put in like 0.99 to a calculator and then you square it and see what happens? What happens to the number when you start taking powers of something less than 1?
It necessarily decreases.
It decreases, and it actually does it rather surprisingly fast, doesn't it? Right? And so if you have n people in there, so that's 365 minus n plus 1, I guess, 365. This number, if n is pretty modest, actually gets pretty small. Now, these are the chances that nobody pairs up on the birthdays. And so the actual answer, what are the chances? At least 2 of them pair up is 1 minus n. Now, n is a bad choice here. Let's call this m. And so as n grows pretty modestly, this starts shrinking fast and you get closer and closer to 1 very quickly. And so even with 23 people in the room, that's the cutoff. With 23 people in the room, you're a little bit over a 50% chance of at least 2 people pairing up on birthdays. And I'm going to use this idea in just a moment, actually. But let me give one more remark about the birthday problem. And the one more remark that I'll give about the birthday problem is one thing that's assumed is that birthdays are uniformly distributed. That is, everybody has an equal chance of having a birthday on any day of year. And this is not true. And in fact, there are certain times of the year, 9 months after holidays and so forth, where the chances of you've got a slightly greater chance of being born on that day. And that actually skews things in my favor. And in fact, my birthday is September 16th, which actually in the United States, as of last year, is the most common birthday. Okay, any questions so far? Okay, so there's a method to my madness that I will come back to in just a moment on this, but let me give you kind of an empty-headed kind of problem here. Toronto. Let me suppose that I'm going to do the following exercise. I am going to dig a huge cubical square out of the earth. It is going to be 664 miles long, 664 miles wide, and 664 miles deep. Actually, a little bit more than that. So for perspective, that hole will reach from here to Toronto, one of the sides, actually 16 miles past Toronto. Okay, so got a big hole, and I am going to assume that all the flat earth videos I watch on YouTube are actually true, that there's no curvature, anything like that. I'm going to assume that this is actually a perfect box that's 648 miles by, or I'm sorry, 664 by 664 by 664. Now I am going to fill this up with little 1 cubic inch dice, just blank dice, little blank cubes. And they're all red, or I'm sorry, they're all white, except for one of them, which will be red, all right? And I'm going to mix that red one in there somewhere. So now I've got 664 miles by 664 miles by 664 miles filled up with 1 cubic inch white cubes, and one of them's red. I will let you pick, I'll put a blindfold on you, and I will let you pick out any cube out of that hole that you want. All right. And in fact, it doesn't have to be on the top. You can go down. You can give me coordinates to where it is. You can pick out any single cube you want. What are the chances that you get the red one?
One over 640 cubed.
Well, yeah, but remember that's in miles, and the cubes are only.
Oh, that's right.
So can we agree on just 2 broad stroke things? The first thing that we can agree on is your probability is not 0. Agreed? I mean, there's a chance you'll get it, but the probability is extremely close to 0, right? The chance of you picking out one out of this is almost unheard of. And in fact, I think we can all agree that the probability of you being able to pick that one red out of all those white when you're blindfolded, very low, right? Now, let me let me change this problem. I mean, it's going to sound like I had a stroke here, but I mean, really, I'm moving on to, this is really similar, actually. The ocean, so this is the number of molecules in one mole of water. And a mole of water is about more or less 18 milliliters, which is about 3/40 of 1 cup of water, or about 3/5 of an ounce. So if you've got 3/5 of an ounce of water, or it's about 1.1 cubic inches under standard pressure. So if you have that many molecules, it basically amounts to about 3/5 of an ounce of water, very small. Number of molecules in all the oceans is approximately 4.5 times 10 to the 46. Right? Now, I am going to give you a little thought problem. Suppose I take that many molecules, suppose I take 3/5 of an ounce of ink, and I put it in a little vial, very small amount of ink, and I go out and I wade into the Atlantic Ocean and I dump the ink into the ocean. And then I get out and I wait 20 years, and we'll assume that the ocean mixes the ink in uniformly, right? So now the ink is uniformly distributed in the ocean. 10 years later, I take a vacation to Hawaii, and I take a vial, the same size of the vial that I first took, and I dip it into the surf in Hawaii, and I hold up this vial of water that I've now gotten out of the Pacific Ocean. What is the probability? What are the chances that I picked up at least one molecule of the ink that I dropped into the Atlantic Ocean years ago? What do you think? Very good? Very bad? Middle of the road? What do you think? Oh, and before you venture a guess, let me point out that there was a point to this previous one with the big box in Toronto, because the ink molecules in all the oceans are roughly the same proportion as that one red cube was in that box that I cut in the ground that's 664 miles cubed. So it's the same proportions. So now, if I dip my vial in there, what are the chances that I get at least one of those molecules? What do you think?
I'd say they're pretty good, because they're on the other hand, while it may be the same proportion as the number of dice, you're not picking one molecule, you're picking a mole of molecules.
You're picking a lot of them, right? And so actually, that's right. Actually, the chances are very good, as a matter of fact. And so let me show you how one might do such a computation, if one desired. You do it like the birthday problem, right? So as David pointed out, you're not just picking one molecule, you're picking a whole mole of them. And that's a big process. So imagine that I have my vial. Don't you love my visual aids? And suppose that I pick out of the oceans here, I start putting in the molecules one at a time, right? I just pick a molecule out and put it one at a time. This will take a while, but let's suppose that I do it this way. Now, what are the chances that that first molecule that I throw in there is not the ink? Really, really good. Same as what are the chances that I pick a white cube out of that big hole in the ground, right? What are the chances that the second one is not the ink? Also really good, right? But every time I do this, I'm multiplying numbers just like the birthday problem, and it starts collapsing. So basically, the computation might be something like this. You might, so N equals number of molecules in ocean. N equals number I dumped. This is the ink stuff that I threw in. And so basically, to miss an ink molecule, I got N chances out of N plus N. And notice that the big N is much bigger than little n. Agreed? And then I've got to miss it again. So now I've got N minus 1 ocean molecules, and I've got N plus N minus 1 of these. And then I've got to pick an ocean that's not an ink again, etc. And I do this until I get down to N minus 1 over N. Let's see, I guess I get N minus N plus 1 over N plus 1. So I've got to multiply all these. Now, even though little n is very small compared to big N, that's a lot of things to multiply. In fact, if you had a computer that could do 93 quadrillion calculations per second, it would take about 75 days to compute this product, right? And so what we can do, though, is we can do this. Notice this product of multiplying things like this is less than or equal to and that one's a little bit easier to evaluate. In fact, you could get a good piece of mathematical software to do this even for large numbers, or one of the things that you can do is you can look at n log n over n plus n. You can do it that way, and basically you can compute the logarithm and then exponentiate it. Anyway, I bounded this on both sides, and so I'll give you all the punchline. Basically, chances of ink were about 1 minus 0.003163, blah, blah, blah. Because you multiply that number, it's less than 1. And even though it's very close to 1, it's enough less than 1, and you multiply enough times to where it shrinks to nothing. So basically, you're looking at about, you're looking at about, what are we looking at? About a 99.97% chance. You spread that all over the oceans, the chances that you get that back is about a 99.97%, even though the distribution of ink within the oceans the distribution of ink within the ocean is about the same as the distribution of that 1 red cubic inch square cube inside that big, huge 600 by 600 by 600 mile pit. I want you all to think about this next time you're sharing a swimming pool with some kid wearing a diaper. That'll keep you out of it. So I'm going to give you all one more thing just to kind of, I'm going to give you a challenge to take home and have fun with. How many of y'all, most of y'all have had Calc 2, right? And what's one of the big things that you do in Calc 2 is you do a lot of integrals and you do a lot of sequences and series, right? That's a big chunk of Calc 2. So here is, so for those of you that haven't had Calc 2, if there's any of you out there, my apologies for this, but maybe the size of the sums might give you a little bit of inspiration here. Okay, so let's go to okay. I mean, this is something that I would actually ask on a test in Calc 2, right, Dakota? I might say, does this or does this not converge? Anybody know?
To be fair, the ones on your exams would be harder than this one, I think. But
Oh, thanks. You know, I got personal stats to maintain, so.
I remember doing this problem. I forgot what the answer was. No, it was literally like in the math 45, 30.
This one actually diverges because you can actually integrate it. Infinity. And I'm not going to use all the fancy limit notation from Calc 2. I'm just going to be sloppy about it. X log x log x dx. And this is log x evaluated from 3 to infinity, which is infinity. So this actually diverges. And you may wonder why I started the sum at 3, but I did that so that it'll be a positive term series. It doesn't need to be for the purposes of divergence, but the purposes of my example, I wanted this to be positive term series. And you certainly don't want to start it at 1 because it's singular at 1. So anyway, since this is a positive term series and it diverges, this adds up to infinity. Now that's kind of unprofessional for me to say, but let me clarify by saying, if you walk up to me on the street and give me large positive number, I can add up enough crap out of this series to where it will exceed whatever number you've given me, right? So no matter how big you want to go, I can go bigger by adding enough terms out of this, right? So this adds up to infinity. So I'll write that in the sloppy notation here. And this is something you can verify yourself. So my question now what happens if you add up a Googleplex of the numbers out of this? That is a lot of terms, right? Remember, like I said, we're adding up a Googleplex, well, actually a Googleplex minus 2. We're adding up a Googleplex of terms of this thing. And remember, that's more stuff to add up than I have got subatomic particles in the universe. How much does this add up to? Well, you can actually bound this by an integral by looking at, right. Actually, I guess I want to do it the other way here. So the sum of this is actually less than 1 over 3 log 3 log 3 plus the integral from 3 to 3 to the Googleplex, 10 to the 10 to the 100th of dx over x log x log x. And actually, you can compute this, and there's so many logs in it that you can actually, the logs actually help you break it down. This is less than or equal to 11.03. So even though all the terms are positive, and in fact, the first term of this is about 3. Actually, it's a little bit more than 3. And the second term is a little bit more than 1/2. But if you add up a Googleplex of those terms, it will still add up to less than 11, even though it's adding up to infinity. So that goes to show you there's a big difference between even a googolplex and the notion of infinity as well. Okay, I think I've kind of rounded out what I needed to do. Any of you good folks out there have any questions? Anybody have any questions?
Not a question, but that was epic.
Well, thank you.
Have you heard of Graham's number?
Yeah, is that the one is it like is that 10 to the 10 to the 70th or something like that? Or am I
No, this
confusing it?
one.
That's
Graham's
the one that came up in the Merton's conjecture, I think.
Yeah. Graham's number is much, much, much bigger than any of
Are
the
you
numbers
talking about that
we've seen.
notation that they use to have the okay, I've got
It
it.
uses like nested arrow notation.
Yes.
Right.
Yes.
Actually, I think I hear somebody volunteering to give a talk about that.
Maybe. I don't know.
Okay, so anyway, so the moral of the story is even very large numbers in my book are kind of abstract. So, any other
so Jim,
questions? Yes, sir.
one of the ways to think about the ink in the seawater is to look at the distribution of the molecules of ink and see what the average number of molecules in whatever size of seawater it was.
Mhm.
And that's going to look roughly like a Poisson distribution.
Oh, yeah, yeah.
And if the mean is big enough, the probability that you get 0 is really small.
Right.
And that might be an interesting way to compute that probability, is how big is the mean number of molecules in a randomly chosen, well-stirred.
Right. Yeah, it is. It is. I mean, I think I personally, even though I've done this talk and variants of it a couple of times, I find a lot of the stuff very kind of counterintuitive, which, you know, and that actually I find counterintuitive quite sexy from time to time. So,
Oh, of course. There's a thing called the Poisson Paradigm, which says if you have really, really, really rare events and you add up enough of them that you get an expected number of them to be moderately big,
right,
then the distribution is almost certainly going to look like a Poisson distribution.
right.
It's a fabulous result from the theory of random graphs.
Yeah. Well, thank you. Other questions? All right. Well, stay tuned for next week when I'm quite sure we're going to have a much better speaker than I. It's going to be a good one. So I hope y'all can tune in for that. If there aren't any more questions, I hope everybody stay safe and take care of yourselves. And hopefully we'll see y'all next week.
Have a good weekend.
All right, thanks.
Yeah.
Jim, can you stick around
Good to
for a
see
couple
you
of
again,
minutes?
Jim.
Thank you.
Yeah, Dakota. Yeah. So are you graduating next year, or what do you think?
Probably spring of 2022.
Spring of
More
2022.
likely.
Sweet. Well, what are you doing?
So I work with Polish groups, so topological groups that are typically bigger than what geometric group 3 people look at.
Okay. Very nice.
Actually, last month I made my first archive submission.
Sweet.
It's exciting.
Hey, when you're at least when you're done with your PhD, you ought to send me a copy of it. Right? That's
Okay.
I'll put that up on my refrigerator, because actually I have graduated 12 PhD students, but one of the interesting stats about me, and this is, and I take a great deal of pride in this, and I didn't think about this actually until a couple of years ago, but you know, I taught all those large lecture calculus at NDSU. So I have 12 of my own PhD students, but I can think of more than 12 students that had me for Calc 1 or Calc 2 that now has a PhD in math or applied math or statistics. And I think that's really righteous. I kind of like that. And you're one of them.
Yeah, no, your calc classes were probably what kept me in the math major because I liked those classes and I did not like the CS classes I was taking at the time.
Right. I got you.
Yeah, and I still think about the exams. Sometimes on a weekend, if I'm bored and I've had a few too many drinks, I go try to do the old ones on your website.
Oh, really?
Yeah.
Okay. So you made my day on that. I think I've occasionally done that myself.
And I've actually suggested them as like challenge practice problems to some of my students when I TA for Calc 1, Calc 2, which admittedly hasn't, it's been a few semesters since I did Calc 1 to Calc 2, but
What are y'all doing now? I mean, are you all online? Are you kind of hybrid mixed or?
yeah, we're all online
Okay.
with like a handful of exceptions, things that you absolutely have to do in person, like the stupid freshman orientation classes, I think have a certain non-online component, and I think maybe like chem labs or something. But
Right.
you have to test twice a week, so that so we all have an app on our phones that links to our student ID that says, okay, this person has tested recently and is allowed to enter the buildings. So you have to test.
Yeah,
we
we test weekly now. Yeah, so I've got to go back Tuesday. So I just get up and go early in the morning on Tuesdays and get her done. Yeah, I mean,
apparently the window's a little larger than that too. That if it's been a week, you'll still be let in for a couple of extra days. There's some window of extra.
Yeah, it's I need, given who I am, I need to forget that window exists to keep me on track. Yeah, it's actually, yeah, I mean, I've tested negative every time. You know, I wonder, I've actually wondered if I've had it, because I was probably one of the last people from Clemson to travel, because I was actually in the UAE in February last year, and it was like right before they stopped travel. And I was with Dakota. Were you there when Richard Hasenauer was there?
Maybe.
Yeah, he was one of my
sure.
graduate students. But anyway, he and I were in